Well, hi there, Nick here, M0NTV, and just to let you know, I'm going to be taking a few weeks off YouTube video making. I've got some holiday planned and all the rest of it, but in the meantime, if anybody is really wanting a homebrew fix, I'm going to share a video coming up right now, which is something I made last year, which I never uploaded to the channel, because it was made exclusively for my own radio club, for the Flight Refuelling Amateur Radio Society, for their annual Hamfest. And it's all about building, testing and using your own return loss bridge. So I will catch you again in a few weeks' time. Happy holidays, and in the meantime, hope you enjoy. It's only 3. Hi, Nick here, M0NTV, and welcome back to my shack and to a FRARS Hamfest exclusive. Hope you're having a fantastic day at Hamfest, spending lots of money, buying lots of stuff and meeting lots of people. And I'm really sorry I can't be with you, but I'm working, so I'm doing the next best thing and making a video to be played. And thank you for coming and watching it. Now, just if you've not encountered me before, I'm a member of FRARS, and in fact these guys got me started on this whole ham radio home brewing journey, really educating me through the 3 tiers of the license, and just encouraging me and inspiring me to carry on. So yeah, great club, and glad to be a part of it. And if you've come across my YouTube channel before, you will have seen that, generally speaking, what I'm doing is designing and building my own SSB transceivers. We're not going anywhere near that stuff today. What I wanted was something simple, but something useful and practical and something interesting, really, that kind of helps us understand a bit more about radio. So I thought, what would be good, it's something I've never built before, is a return loss bridge. And it's a really simple little thing. It's a little simple resistive bridge. It's just basically 3 resistors, a little transformer, which is like a balun really, and 3 RF connectors. But why it's useful is that what you do is you squirt, technical RF term, an RF signal into the source port. You have a load on your load port, and then on your measuring detection port, you can detect how much signal is reflected back from the load because of an impedance mismatch at the load. So you can see, how much of your signal is actually getting through to the load. So if this sounds familiar, you think, well, isn't this like SWR? Well, yes, and it's all related, and we'll look at these different terms as we go on. But actually, return loss, although a lot of hams don't talk about return loss, it's a shame because it's actually a more useful thing to talk about very often than SWR, particularly because it's measured in decibels. And of course, you can kind of stack them up, you can add them and subtract them. So one of the ways you can use a return loss bridge is on a coaxial run. If you want to know how much loss is in this coax, and it might just be a short bit of coax, but you can terminate it at the other end, stick it on. You can obviously use it on antennas to see whether you've got a good 50 ohms match, or you can use it on anything really that you want to determine whether you've got a good 50 ohm match or not. So it's a useful bit of kit. You can also do something completely different with it, which we're not going to cover in this video, but it's identical to what's known as a directional coupler. So it's a useful bit of kit to have around the shack, and it's not too hard to make. So let's have a look at the schematic, and I hope you find something of interest here. So how does this thing work then? Well, let's have a look at the schematic. Apologies, it's a little bit pixelated here, but you get the idea. So you've got your RF source here, and what we've got is a 51 ohm resistor here, and a 51 ohm resistor here, and a 51 ohm resistor here. So this is forming this resistive bridge, and this load is acting as though it were the fourth 51 ohm resistor. If it is indeed 51 ohms, then actually the whole thing is balanced and nothing flows, or almost nothing, flows to the detector. This transformer is actually functioning as a current balun. And you perhaps understand a little bit about balance from an antenna kind of point of view, but the principle is just the same here. You're taking a balanced input, so you're not talking about like a voltage line and ground or anything. You've got two inputs here, so you've got a balanced line coming in here, but you're coming out to a centre pin and to ground, so that's an unbalance, like a bit of coax, so that's what it's doing. It's just converting the balance to the unbalanced. And if you had 50 ohms on here, or 51 ohms, it would be balanced and you wouldn't get anything flowing there. But the more unbalanced this is, if you like, so that the more this deviates from 50 ohms, the more of your signal is going to find its way through to the detector. And that's really how the thing works in a nutshell. A clever little thing, and not very many components. So we're going to have a go at building one. And as the most complex thing on here, these will just be 3 BNC connectors, obviously just 3 resistors, which will be easy enough to solder in. The most complex thing is the transformer, and that's what we're going to spend most of the time building, and I'm going to show you exactly how I do that. So let's crack on.
Well, welcome to the bench, and the most important thing, the thing we're going to start with, which is the thing that, funnily enough, fears most people, is the transformer, which, as I think I said before, is really a one-to-one current balun. And so we're going to start with just a tiny little FT3743 ferrite, and on that we are going to wind 10 turns bifilar. What is that? Well, essentially it's 2 wires wound as though they were one through there. Now the easiest way of doing it is to get yourself some bifilar wire. So this is thank you, Sota Beams. So this is their stuff. So now I'm going to try and zoom in on here. So this is actually 2 strands. I don't know how easy it'd be able to show you this, but actually you can probably just see if I can balance that and get that to focus. Yeah. So you can see there's 2 colours. There's a red and, well, it looks black, but it's actually a green. So you've got red and green, and that will help you when it comes to actually wiring it up, because you can see you've got 2 different colours. So what I'm going to do is I'm going to take a strand of this bifilar wire, and first of all I'm going to twist it, and I'll show you how I do that. Right, okay, so I've cut off, well, that's plenty for 10 turns, probably far too much. And you can see what I've actually done here with the Stanley knife. I've just gone and separated these 2 about 1 inch or so, and the same on the other end. Now what I'm going to do is this end, and it doesn't matter where you start, but this end is going to go in my vise on my bench, and the other end is going to go into the chuck on my cordless drill, and I'll show you what that looks like. So you can see you've got one end in the vise, the other end is down here. Now what I found was, because this wire is so thin, it was just spinning around in the chuck, so I've had to kind of fold it over a bit to just make it a bit more bulky, so there's something that the drill bit can actually get some, the drill chuck can get some kind of purchase on and hold it tight. Right, well that did the trick. So I've got that in there now, and that in there. So all I'm going to do now is, and now I'll try and set the camera up so you can see this, but I'm going to set it to a really low setting and just very slowly just rotate it. And what it will do is just put some even turns in that wire. Okay, so hopefully you can see what I'm going to do here. So I'm just going to hold this and just slowly put some turns in. I think that looks about fine to me. So hopefully you'll be able to see. What we've produced. So there you can see we've got our even turns spread all the way along the wire, and that's exactly what you want for your bifilar windings. And talking of windings, that's what we're going to do now. So winding time now, and this is what fears people. I don't know why really. It's pretty simple. Once you've got your bifilar, so I've kept these ends, these long ends here open, and I've just twisted these together just to make it easy. So we're going to go through the toroid. Now the thing to remember when you're winding toroids is every time the wire, or in our case wires, passes through the toroid, through the centre of the toroid, that constitutes one turn. Okay, so what we're going to do is I'm going to move it all the way down to the end where my long ends are down here, and I'm going to start there. Okay, so now the hardest thing actually is the first few turns. After that they tend to stay put a bit. So that I'm going through one, so I'm going through for number 2. So you're just going to poke it through. Now try not to get it. Easier said than done. And bifilar is hard. Trifilar is even harder because the wire is very stiff. But get it through. Don't cross them over. So just make sure you've got nice turns. And then when you've got that one like that and one like that, you can pull it tight. Hang on a minute. Okay, so now can you see? Let me put it down. It might be a bit easier to see. I've now got my 2 turns because the wire comes in here at the back, comes through once. Let's start here. It comes down here, goes through, out again, 1, goes through again, 2, and out again. So that is 2 turns. Now, let's do 3. And you'll find, once you've got the first couple on, it gets a lot easier. So pull them tight, keep them together as best you can, like that. Okay, so that's 3. 4. 5. Okay, so you get the idea. So I'm not going to count off every turn because that'll be very dull indeed. I'll see you when I get to 10. Okay, so that's my 10 turns. And you can see I've got plenty of space. In fact, I'll be cutting these leads right down. That's all right. And notice I've left a bit of space down the bottom. Now, if you can do that, it's a good idea. I mean, I would normally aim for, well, a quarter or a fifth, possibly, but if you can, you want a little gap just down the bottom with no turns on. And the reason you do that is just to put a distance between the in and the out, because you can get a mutual capacitance when these ins and outs are very close together. And when you've got a lot of turns, that's kind of hard to do. But do your best. So that is it. So what I'm going to do now is chop these leads down and these I'll have to separate, which basically just means going with the Stanley knife and pulling them apart and then cutting them off. And then I will need to prepare the ends of the wire. What that means is two things. I get the Stanley knife again and I scrape this enamel off, and it's easiest to do this with this coloured enamel coated bifilar wire, because you can see, you know, because the green, when you're not seeing any green and you're just seeing the shiny wire itself, you know you've got it off. Or if you're still seeing bits of red on the red wire, you know you need to kind of work harder. So it's kind of easier to do than with kind of standard enamel coated wire. So do that. So scrape it off, then heat up your soldering iron nice and hot, big blob of solder on the end of the iron, and just go up and down it. Hold that iron on it, and I might be able to show you that in just a minute. That will do two things. That will burn off any enamel that you missed, and it will also tin the wire, which will make it easier to solder into your circuit. So that's the next job. So I have scraped those leads now. You can see I can cut them off to a more manageable size. So now, yeah, we're going to tin them. Okay, so get a nice screaming hot soldering iron, and you're going to do everything they tell you not to do when you learn how to solder. You're going to put some solder on the iron itself. You're going to put some on the wire as well. So let's go for this one and put it on. Nice big blob. Hold it, run it up and down. Don't breathe those fumes in, which is easy to say when you're videoing. I've got a door open here. Right. Let's try that again. So you should be able to see now, yeah, that is definitely well tinned. And so you basically just go round and do them all like that. So we'll just do this one and then call it quits. So you're just taking off any enamel you missed, and you're nicely tinning that wire for when it comes to actually soldering it. And the final test, which I would always advise, is the continuity test. So get your multimeter, set it to the continuity setting, and we're going to go in here. Now you're going to make sure you can see which one's which actually is not as easy as it looks here. So that looks like the red here. So that's a green, that's the red. Yeah, it's not even showing anything on the multimeter, which is great, it's so low. That's the other end. So now let's do the green. That's the green. So you shouldn't have anything there. That's the other red, that's the other red, and that's the other green. Yeah, so really well made in terms of continuity, so that's good. And we're not kind of shorting anything out or whatever. That can happen sometimes with this bifilar, hard to say, wire. When you pull it apart, sometimes you can actually pull off some of the, sorry, door shutting, the insulation, and if you're really unlucky, you can end up shorting these wires together with it, and it's a real pig to find out quite where you've done that. But just be careful. But yeah, so that's good to go.
Well, once you've built the transformer, I mean, that's the most difficult bit. All you got to do is put the rest of it together, which ain't going to take you long, because there's not a lot to it. And here's one I prepared earlier. So as you can see, all it is just 3 BNC connectors and 3 resistors. And so, yeah, went together pretty quickly, and I just built it on an old little scrap of double-sided
copper clad board. And so the way I've arranged it, actually the transformer sits nicely in there, and notice that little bit at the bottom without any windings on, that can sit on the ground. There's no danger of shorting anything out or anything like that. Tried to keep the leads as short as possible, because that's always good, and that will improve the kind of the linearity over a wider bandwidth if you can do that. But just knocked it together, really. There's not that much finesse. Really, I'd ordered a little tiny little metal box. I was going to put it in that, but to be honest, I couldn't wait. I just thought I'll knock something up and see whether it's any good. And so I did. So this is it. So all we've got to do now is rig it up and test it out and see how it works. Well, the easiest way to demonstrate how this works is to use the spectrum analyzer. There are other ways, don't panic, but that's the simplest way because I can just kind of show you the screen. And effectively what we're doing, as I've mentioned before, is we're putting an RF signal source into the source port, that's the S1 on the left. We're going to put a load on the L port there, and at the moment it's just open circuit, as you can see, and then we're going to put some measuring device on the D on the detection port. So what I'm using at the moment is my spectrum analyzer, because this has its own tracking generator, and this means I can use the tracking generator source there as the RF source going in to the S port, and I can connect the D port, the detector port, to the input of the spectrum analyzer. Right, now what you're seeing here on the screen, and remember we're open circuit at the minute, there's no load on there at all, so when you think about it, this is as bad as it's going to get in terms of the amount of reflected signal, because there's not even trying to get any kind of impedance match. So let me just kind of going around this thing. Let's just get in a bit closer. Now what you're looking at here on the screen is a 1.5 gigahertz span of what it looks like open circuit, and obviously we're not interested in that full amount, and for me I'm really only looking at the first bit, and you can see it goes up and down, but actually if we change the span, let's just go into the frequency, we'll start it at 1 megahertz and let's stop it at 200 megahertz. Now look at that, and if I put the average on, yeah, look at that. Now that's not bad at all in terms of linearity, right from 1 megahertz to 200 megahertz. So that's pretty good. And in actual fact, it's less than half of that really that I'll be actually really interested in. So what I'm going to do is I'm going to narrow it down a little bit more now, and then we're going to do some experiments. Okay, so what I've done is I've zoomed in now, so I'm going from 1 to 50 megahertz, and that's pretty flat, which is great. That's what you want to see. So that's still with the open circuit, which, as I said, will be the maximum amount of reflected signal. So let's try it now with a perfect match. So with a 50 ohms termination on that load, and I'll do that now and show you what that looks like. So you'll see I've attached a 50 ohms load onto the load port now, and let's have a look at the screen. So you will see I've got the unloaded trace on the top, that's the yellow, and then the loaded trace is the bottom one in the kind of pink. and you'll see my markers at the top right. So we're actually getting just over 35 dB of separation between those two, which is pretty good, actually. I think the gold standard they go for is 40 dBs or more, but so 35 is pretty good. I'm quite impressed with that. And so effectively what you do with this to calculate the return loss is you're comparing the separation basically between those two traces. So the top one won't change because that's the maximum amount of reflected signal you can get because it's an open circuit. You could do a short as well, but I've just chosen to do an open. And the bottom one that will change depending on your impedance match. And so that's the perfect match. So it's not going to go any lower than that, but it will go higher. So the more separation there is between those two lines, the better return loss and the lower VSWR you will get. And I'm just going to demonstrate this now by putting a load on to the load port, which isn't 50 ohms. And so you can see, so the top trace, of course, is unchanged. That's the unloaded trace. And then the loaded trace is below. Now, if you look at the top right, you'll see there, so the marker 1 is on the unloaded, is still minus 32.95. Marker 2 now is on minus 42.60. Now what I've actually done, and if I can, I can probably just show you down here. Yeah, I can. What I've done is I put a 100 ohm resistor, a big chunky 2 watt one, across the port from the center pin to ground. So now that should, all things being equal, correspond to a 2-to-1 SWR, and we'll see because we'll get to the calculations in a minute. But if you note those values in dBm, and I'll write those down, and we'll get to it, because actually if you're using a spectrum analyzer or anything really that measures in dBm, it's a bit simple. You can jump over 2 stages in the calculations, but we'll get to that. But let's do it properly first as well. So I'm going to change now the units from dBm to volts. So you see I've changed the units to volts now. So marker 1 is sat on the unloaded line at 5.03 millivolts, and these are RMS values, and the pinky purple line with marker 2 on it is sat at 1.66 millivolts. And we'll get to those in a bit. Now I know what some of you are thinking. Well, that's all great if you've got a nice flashy spectrum analyzer, but what if you haven't? Well, I'm glad you asked, because there's many ways you can do it. So basically, this return loss bridge is just the center part of a 3-part measurement system. You've got your bridge that you've built. You need some method of RF generation, and you need some method of RF detection, but those methods can change. So what you could use, if you've got one, is a signal generator. And now this is a digital one, but you could use an analog one. Use whatever you've got, and it doesn't need to do a sweep. It doesn't need to be like a tracking generator. You can just put a single sine wave, as I'm doing now. So I've got a 25 megahertz sine wave, 140 millivolts peak to peak, and and that will do it. Now, bear in mind, you'll only be measuring the response at that particular frequency, but that's fine. Particularly if you can change the frequency, then you can work your way through your frequency of interest. So I'm using my signal generator, and I'm then going to the return loss bridge, but then I'm going to my tiny SA, and let me tell you, this is a lot cheaper than the Siglent that it stood behind it, and does remarkably well. And so what I've done is I've like I did with the Siglent, I converted it from dBm to volts, and you'll see. So this is the again, this is the open unloaded voltage, and we're measuring there. You can see 5.3 millivolts, and I'm just going to connect the resistor and see what it's like loaded with the 100 ohms resistor. Okay, so we've got the 100 ohm resistor on now, so let's have a look at the tiny SA, and 1.58 millivolts loaded, and so I'm going to make a note of that, and you will remember, so we've just measured 1.58, which is very similar to the 1.66, and we've just measured 5.3, I think it was, which is very similar to the 5.03. So you can tell already that even though we're on a much cheaper and lower resolution instrument in the tiny SA, it's pretty close to the much more expensive bigger brother that it stood in front of. Right, well, let's say you don't have a spectrum analyzer of any form. Well, you might have an oscilloscope. And if you have, you can use that. Now this time I'm starting the opposite way around. I'm starting with the 100 ohm resistor on. You need to pump up the volume a bit with this, because if your oscilloscope is anything like mine, it won't detect those very low levels of voltage that even the tiny SA can. So I've set 4 volts peak to peak, everything else the same, 25 megs sine wave, going into the return loss bridge, 100 ohm resistor on, and I'm seeing, well, let's call that 108 millivolts. 108 millivolts, right, I'm going to write that down. That would do. If I could find a pen. Oh, hang on, it's over here. Right. Loaded, 108 millivolts. And so I'm just going to pull the resistor out now and wait and see what happens. Okay, so there, 328, let's call it 328 millivolts, and I will write that down. So there are many possibilities. If you haven't got a flash signal generator like that, I mean, that's not particularly flash signal generator, but you know what I mean. You can get analog ones, you can get cheaper ones. You just need something. If you're being tempted to use your rig, just be very, very careful, because even on 5 watts, you'll absolutely melt those resistors. So now you could build this thing with those resistors. In fact, that's why those resistors are lying around, because I was going to double up 2 of those 100 ohm resistors, which would give me a capability of 4 watts through each pair then. So you could do that if you're going to put some more, but you might have to beef up the transformer as well. So just be very, very careful with that, unless you've got some good attenuation, because really you don't want to be putting that kind of power through it if you can help it. But it's an option as long as you're careful. How you detect it if you don't have any kind of oscilloscope or any kind of spectrum analyzer or anything like that, you can use something like this, which I built, and all this is a simple little diode detector. It's kind of really the kind of back end of a crystal set, really. You know, it just takes the signal in to a voltage divider, splits it, then goes through that diode rectifies it, so you just kind of get one half of the waveform, and you've got a capacitor to ground there as well, and you can put then your multimeter terminals on there. It kind of works. There are formulas and things for doing it. I'm not going to go into that now. That's a whole video on itself, really. The problem with all of that is, and I've used a germanium diode that has a very low forward voltage drop, so I'm not really wasting much signal, but it's the way the diode behaves at different levels of current, and so it's hard to get the same level of accuracy as I've shown with these other methods. But hey, you can get it to work if you need to. So and there are many other ways as well. So this has just been a few. But what I'm going to do now is we're going to have a look at all these numbers I'm scribbling down, what they actually mean in terms of your return loss and your SWR, and ultimately what kind of a match you're getting with your load to your signal source.
Okay, let's do something with all those numbers I've been scribbling down when we were experimenting. So let's turn them into something useful. Right, so first of all, just some terms so we know what it is we're measuring and calculating. So remember, the maximum output on the detector port is when the load is either open circuit or short circuit, and we did an open circuit, which makes sense when you think about it, right? Because, you know, that's when you're going to get the most reflected signal back to the detector port. Now, this maximum output, this is the reference point against which we measure, well, everything else. So basically there's four terms which are significant here. So the first one is denoted by the uppercase Greek letter gamma, which is the reflection coefficient. Now this is actually a complex number, so it's a vector really with a real and imaginary part. We don't need to bother about any of that stuff. In fact, all we need is what's known as the magnitude of the reflection coefficient, which is denoted by the lowercase Greek letter rho. Looks a bit like a kind of curly P, but it's an R sound in Greek, which is called the magnitude of the reflection coefficient. It's measured in volts. Then you've got the return loss, and actually all the return loss is just the magnitude of the reflection coefficient expressed, instead of in volts, logarithmically in decibels. And then the one we're all familiar with, the voltage standing wave ratio, the SWR as we would call it. So those are the other terms. Here are the equations. Now, full disclosure, you don't need to do all these things by hand. This is just if you're weird like me and you're interested in working it out. But actually, all you've got to do is Google return loss bridge calculator or something like that, and you will get lots of websites, and there's some very good ones that you can just plug in one of these parameters and it will work it out and let you have the other ones. But if you are interested, then here's how it's done. So you start with rho, the magnitude of the reflection coefficient, and all this it's the loaded voltage, so the voltage you measure with your load, whatever that might be, attached, divided by your open circuit voltage, and that is measured in volts. Your return loss is simply that you've just calculated, and you take that and you go 20 times the log of the magnitude of the reflection coefficient. You're just converting it to dB basically. Now for SWR there's all kinds of different ways of calculating that, some of it far more complex, but the simplest one is if you know the magnitude of the reflection coefficient. It's just, the SWR is just 1 plus rho over 1 minus rho, and that will tell you instantly what the SWR is. So let's try this out with our example. So you remember when we use the spectrum analyzer, and these are the results I measured on the Siglant, but you'll remember the ones that we got from the Tiny SA were really very similar. And in fact, although the voltage levels were different when we used the oscilloscope, actually if you plug those values we got from the oscilloscope into here, it works out exactly the same as well. So it does in fact work. So we measured a 1.6 millivolts. We divide that by 5.03 millivolts. So that gives us a row of 0.330 volts. And so we go 20 log 0.330 gives us a return loss of minus 9.63 decibels. I'm not going to go into all the things. There's a raging battle about whether return loss should have a minus in front of it or not, but I'm just not going to go there at the minute. It doesn't make any difference for our point of view. It's the actual value of it which is significant. Now you can look this up online. There's tables that you'll find as well that will equate all these different things. But if we just take the value for rho that we got and stick it into our equation on the right here, so 1 plus rho over 1 minus rho, and if you do that, so 1 plus 0.330 over 1 minus 0.330, then you get 1.98 to 1. Which, if you remember, with a 100 ohms load, if everything was perfect, you would expect to see a 2 to 1 SWR, and look at that, 1.98 to 1. So you can't moan about that. So, well, hey, it actually works. So there you go. I hope that you found something of interest here, and if you have enjoyed this video, then please do look me up. If you Google M0NTV, then you'll find Top Hit is my YouTube channel, and I'd be pleased to see you. So thank you very much for watching. Enjoy the rest of Hamfest, and 73. Bye bye.